Okay guys, so what I want to do is for 460 I want to demonstrate how we use the new TramelBlaze. I'd like to show how we organize a project, how we create the software to run the TramelBlaze, how we assemble it, and then how we can simulate and how we can then eventually generate the bit file. So just as a note, I went ahead this morning, I've run the same project on a Nexus 2, a Nexus 3, a Nexus 4. My Nexus 2 I did on my Windows 10 machine. The 3 and the 4 I did here. So what I'd like to demo now is the Nexus 3 with the PicoBlaze. So the first thing I'd like you to do is in your project directory that you're working in, have an assembler directory set up. In the assembler directory, copy the TramelBlaze assembler, the Python tool, and then generate your TramelBlaze assembly file. For us right now, I have a very simple routine that will service the interrupt and then output to 1234, which we've set up as the address for the register that we display on the LEDs. So once you have your assembler directory set up with the TramelBlaze assembler and you've created your assembly file, go ahead and launch the assembler. Then you have to type in the name of the file, which is for us here project 1460 blaze.tba. When we run it, it'll generate several files. The list files to help you debug. The sim file is the previous version. I'm probably going to stop generating that. The COE file is the file that we'll use when we create the memory using the core development tool under the Xilinx ISE. So once you have your core, your COE file, now we can go back. Now we want to set up a project. So I have all the files here, so I'm going to go ahead and launch the Xilinx ISE 14.7 64-bit navigator. Not sure who will come up, but I'll close the project when it does. So once it comes up, what I want to do is close this project. Now I want a new project. And my new project is going to be in my 460 Blaze in3 directory. And I'll call it project 1 460 Blaze. Might as well put the N3 in as well for the Nexus 3. Make sure that you set up for an HDL. Make sure now this is set up for the correct device. This is the Nexus 3. I believe this is the correct setup. Spartan 6, XC6SLX16, CSG324. Next, finish. So now I've set up my project. Now I want to add the sources to the project. So all of my files, including my UCF, I want to add. Now, before we dig in, what I'd like to do is show you the architecture. So the TramelBlaze top is what we instantiate in our design now. Within it we'll have the processor core and the memory. So first, let's look at the processor core. And it has exactly what you had before. It has all the ports for the TramelBlaze, including the address instruction, which will be the interface to the memory. The problem we have is that we don't have a memory. So to create the memory, what we want to do, we want to come and say new source. We're going to generate our core. And the file name we want to generate is TramelBlaze ROM. Now, creating it's going to take a little bit of time. Bear with me, but we'll see how to do it, and then you'll be able to do it yourself as well. So once it opens up, we choose the memories. We choose RAMs and ROMs. And we're going to choose the block memory generator. Then we say next and finish. So now the tool is going to run. It's going to generate the shell for the memory. We're going to come in and configure it to tell it that we want a ROM, how big our ROM is. So that's the correct name. Next. Here we want to choose a single port ROM. Here is where we configure the size. The peak TramelBlaze is set up right now for a 4K deep 16-bit wide memory. We don't want to add anything other registers. Now we want to load the COE file, which will provide the contents for our instruction ROM. So now we move back up the hierarchy, find our assembler, then we select the COE file. Then he'll say, got it. I think we're ready to go. We don't need to say fill it out because this COE file has every memory location in the 4K generated. Next, now we just say generate. So what's happening now is that it's creating the model for our TB-ROM that we'll be able to use both simulating our design and implementing our design on the Nexus 3 board, which is what the example we're using is going to use. Again, it takes a little bit of time, but I'm going to let it run just so you have a feel for how long it takes. The nice thing is when you've created your ROM and then you want to update the contents of the ROM, all you have to do is regenerate the COE file. Then you come back in and say regenerate, and the code will build the ROM again with the new contents from your COE file. So once you get up and running, it's a little bit easier to upgrade the contents of your ROM. Again, what we're doing is we're generating the ROM that will let our processor run. So we can see that we finished. Let's go and do a simple simulation. I have a test bench. In my test bench, what I'm doing is pretty simple. I set the up, high, down, low. I set my switch and wait, turn it off. So I'm allowing maybe 10 cycles. Oh, I'm glad I looked. Then I want up, high, down, low to go low. and then I want to continue running. So I should see my guy count up, then I should see it count down. So there is a very simple test bench. So now I want to select my test bench. Let's do a quick behavioral check. I may get a few mismatches on the buses, but now let's run the simulation. Now this is done in lieu of having the readmem H. So now we're in the simulation. What I'd like to do is go ahead from the processor's perspective and let's add. So let's come back over here, cut all these, and let's grab everything here on the interface to the processor. So now I want to Control A, put them all in a hex radix just to make it a little bit easier to look at. Reset. Now I want it to run a while. So this is going to be a while. So let's run it 500 milliseconds. Now, as it's running, what we can do is just wait. We can look at the signals the way I've named them in my design. There's the reset. That's the switch in, up high, down low. There's the 4 anode bits, the 7 cathode bits. What I've done in my design is not only am I driving the 7 segment display, but I'm also driving the LEDs with the eight least significant bits of our count. The count in this case is being maintained inside of the processor. The import, because we've tied everything to up, high, down, one, down, low, is all ones. There'll come a point in time in the sims when it should switch to all zeros. And let's take a look and see. So I get a little feedback now. So I can look at my count. This is the counter. It's really not the counter, but it's the register in my design that the TramelBlaze is writing with the current count. At this point in time, my count has gone up to 2. It's probably good enough. I don't need to sit here too long. If we come and do a full view, we can see that I'm updating as we go. My debounce is coming in on every pause edge. I'm generating my pulse and incrementing my counter. So I can tell right now that from the simulation, things are running pretty well. The next step would be to go ahead and leave the simulator. And now what we want to do is want to come back and go to implementation. This time we want to synthesize the design to generate the bit file. So what I'd like everybody to do is each time you generate a bit file is to right click on the generate programming file and go to process properties, startup options, and always choose the JTAG clock before you build your designs. So now what I'm going to do is I'm going to go ahead and run to generate the programming file. It's building my design, including my top, my processor top, my TramelBlaze processor, with the code from the COE file that I loaded. And when this runs successfully, what it's going to do is generate a bit file, and we'll make sure that I get the bit file. Then what I want to do is program the board. And what I'm going to have to do is take a video of that and I'll append it on the end of this presentation when I post it on YouTube. So again, it's a little slow, but demonstrating it I felt was a way for everybody to see each of the steps, see what's going on. I'll accompany this with a very simple write-up that documents what we're doing as well. So I'm going to let this run. Once it generates the bit file, then I'll go ahead and stop the video, and then we can see what happens when I program the board. So maybe I'll go ahead and stop now since I'm kind of running out of things to say. So here we are now. There's the bit file that was generated a few minutes ago. So what I want to do now is choose it. Then I'm going to program, whoops, my board. Now my board has been programmed. If I do this right, my up, high, down, low is a 1. The reset. Counting up. Change up, high, down, low. And so we can see it goes, then there's my reset. Now the one anomaly I've noticed is that starting up, it took a reset or two to get going. So I'm not positive what's happened in the initial case, but once I get past that, everything's working pretty well. So right now you guys should be all set, ready to go.